There we all are. Hello. Everybody's so excited. See themselves. Here I am. I'll give everybody a second to get your stuff out and get situated or whatever. We've got like 4 minutes. All right, I got some stuff to pass out and then we'll be good to go. You got it. Okay. Excellent. Everybody got their goodies from Annabelle, right? Good. All right. That was very sweet of her. Yes, ma'am. Oh, look at that. All right. Okay, are we ready, people? Yes. All right, so we are doing now. I don't know if Lucas and Xander might try and join this. If y'all will see them before I do, because I tend to not notice. But if you see them like trying to knock on the door and come in, yell at me and I'll let them in. All right, so reversible reactions and equilibrium, systems at equilibrium and equilibrium systems and stress. Today we stressed a system at equilibrium, didn't we? Yeah. Yep. And shifted it around a bit. All right, so first, now you've noticed your notes look a little different, don't they? Yeah, suddenly it's a little more demanding. You got to figure out how to take the notes. I do that in chemistry in particular because it's good for you to learn, and this is probably the best subject, best class for you to practice that skill in. But when you get, for those of you that go to college, when you get to college, you may get slotted notes like I give, but probably not. You're going to have to go through your text before class usually, and it's good if you come in with your notes done, meaning you've read ahead and you've learned to outline. Is everybody familiar with traditional Roman outline, like Roman numeral 1, A? Yeah, Arabic numeral 1. Yep, you're familiar. Okay, so I'm a big fan of that because I think it's an easy way to organize, and it's clear, and most people can learn to do it on their own. So your notes are kind of, especially fourth quarter, they're really set up for you to do that on your own, like to go through and write out your own definitions to find the important things. By the time you get to fourth quarter, it's not even as set up as it is here. It's just like, here's your heading and a blank section, and you got to figure out how to do your notes yourself. And it's important for you to learn to do it. It's a little more work, but it's important for you to learn how to do it because one day you're going to need that skill. So just practice it now, like really practice it. Because, in this class, it's not going to hurt you if you didn't do the notes, but it's sure not going to help, right? But it's a good thing to practice now so that when you have to do it for college or whatever, if you decide to go, it works for you. All right. So moving on, complete reactions and reversible reactions. Reversible reactions in equilibrium. So what is a reversible reaction? Caitlin?
A chemical reaction in which the product reform the original reactant.
There you go. Okay, so it's a reaction depending on ambient conditions, ambient meaning your pressure, your temperature, right? Your concentration, that can proceed in either of two directions. The production of the the production of the reaction products from the reactants, or the production of the original reactants formed from the reaction products. So it can go forward and backward, which we saw today in class. Some reactions you cannot go forward and backward. When something combusts, it combusts, right? You can't undo that. But there are a lot of reactions that you can force to go either direction. So reversible reactions and equilibrium. What is chemical equilibrium? Who has a definition for that? Caitlin again.
State about where the rate of a forward reaction equals the reverse reaction and the concentration of the products and reactants don't change.
Very good. So a state in which the rate of the forward reaction equals the rate of the backward reaction. The rate, what is rate? Who remembers what rate is? Who say it again? What? No, Drew? That's one way to do it. Yeah, distance divided by time, or basically in this case, your rate is like your production of products or your production of reactants divided by time. So it has to do with rate is going to involve time. It's basically how fast something's happening, right? Or how slow something's happening is your rate. So there is no net change in the concentration of reactants and products, which is what Caitlin said. The amounts don't change. And this kind of equilibrium is also called dynamic equilibrium. So here's your goofy little comic, and it says, I'm sure glad they evaporated. We're back. So basically, you've got, these are water molecules, right? You can tell because they look like Mickey Mouse. Water molecules look like Mickey Mouse. And some of them are coming out of solution, and some of them are going back into solution because you have a certain level of dynamic equilibrium here. And this does happen on the surface of liquids. Now, something I didn't show you all, but I will real quick. So our hydrochloric acid that we used for this lab today was 12 molar, which makes it about 37%, which for hydrochloric acid is pretty strong. And if you look at the outside of this bottle, you can see it's like, it's messed up the label, and you can probably see there's like a film, and it's sticky. Acids tend to be sticky. That's because it's so concentrated that it will evaporate to some degree. And when it evaporates, it's the acid that's evaporating. And it will come out of that bottle and collect on the outside of the glass. So you should expect your acid bottles over time, they will start to look like that. They will make their way out around the inside of that cap. Lemon juice, yeah, does lemon juice do that too?
Not very often.
I was gonna say it's probably not strong enough to do that, but that hydrochloric acid is 37% is pretty strong for hydrochloric acid. And when you open up hydrochloric acid that's that strong, you can see the vapors. You probably couldn't see them in your very tiny vial, but if I opened up that bottle, you can see it coming out. And you can smell it, and it will burn your eyeballs, and it's like, whoa, like it's very, very strong when you open it. So when I opened it for the first time in 4 years the other day, it was like, you could see it all coming out. It's wild. So what do we talk about when we talk about opposing reaction rates are equal at equilibrium? So you've got your forward reaction, right? And it starts fast and it slows down. Your backward reaction starts slow and speeds up, and then they reach equilibrium. So chemical equilibria are dynamic. What does dynamic mean? Anybody know what dynamic means, Jordan? Yeah, change. It can change, right? You can say, like, people talk about people having dynamic personalities or whatever, like they're just kind of everywhere. They can change. So here's an example. You got two people snow blowing, and he's blowing snow and it's going this way, and she's blowing snow and it's going that way, but they're supposed to be clearing the sidewalks and it's not working because she's refilling his sidewalk and he's refilling hers, right? Great example of dynamic equilibrium. There's another one down there, which shows an actual chemical reaction. And then This would be Ozzy trying to go somewhere, right? And me not moving and him moving. That is dynamic equilibrium as well. You can see it right there. Like he's not going anywhere, but he thinks he's going somewhere. So, legs are moving, but we're not getting anywhere. Kind of like trying to walk up the down escalator. Anybody ever done it? It's fun, right? It's fun, right? You look like an idiot, but it's great fun. You're going, but you're not going anywhere. Right? You gotta go, yeah, you gotta go real fast. Gotta take big bounding steps if you want to get up it. Yep. Yep. Some more examples of equilibria. Without chemical equilibrium, life as we know it's not possible. Another example of equilibrium in our bodies goes on every day. What's this example from your book? What's the macromolecule that transports oxygen around your bodies? Hemoglobin. Very good. Okay. So hemoglobin is a macro. What is macromolecule? Big, macro, large. Yeah, it's a large molecule. And it transports oxygen around your body. So it's in your red blood cells, right? Without it, we wouldn't survive. Hemoglobin has to be able to take up oxygen, but it also has to be able to release it. And it does that through changes in chemical equilibrium. And it takes place in different places in your body. So right here, you've got your red blood cell, and it takes up oxygen from your lungs. In this case, the oxygen are the little blue dots. And in they go, pop, pop, pop. Your little hemoglobin molecules here are the little kind of pinkish dots. So it's going to suck up that oxygen. It's going to bind as it flows through your body. And then when it gets to the tissues that need the oxygen, it's going to unload that oxygen into those tissues. And we call when it holds the oxygen, when it's oxygenated, we call it oxyhemoglobin. And then it lets go of the oxygen and it's hemoglobin. So this is also what makes your arterial blood bright red. So blood that's in your arteries is very, very red because it contains oxyhemoglobin, and it actually produces that color in the pigment here. So what's an erythrocyte? Anybody know? Erythro means red. Cyte is a cell. That's a red blood cell, is an erythrocyte. Leukocytes would be what then? Anybody know? White blood cells, yeah. You can have, for example, you'll see LEUK or LEUKO for leukocytes in your body, but you'll also see it in nature when describing, for example, like when we talk about humans that lack melanin, that have a genetic defect that lack melanin, what do we call those people? Do you know? There's a word.
Is it?
There's a word for that disorder. Do you know, Drew? Albino, right? But we don't call birds albino. When birds lack melanin, if it's a type of bird that's like if it's a cardinal, but your cardinal's white, they call them leucistic, I believe is the word. Yeah, what does it say again? Leucistic. Yeah, I couldn't spit it out for a minute. My brain lost it. Yeah, leucistic. So actually I saw a picture the other day of a female cardinal that was white, but her beak was still bright orange. And so basically it's the same type of genetic defect. It's a lack of pigment, but it's different in birds. We use a different word, but there's that LEUK again. There's that root again.
Isn't it called vitiligo in humans or something like that?
Vitiligo is when it's patchy. Yeah, vitiligo is patches. So you can have patches where there's pigment lacking, and you can see that very often in certain people. It's yeah, and it's far more common than straight albinism in humans. But does anybody know anybody with albinism? I know one person with albinism. Yeah, and it's pretty wild. Yeah. So now it's a challenge. Albinism comes with challenges aside from just the lack of pigment. They tend to have vision problems and other things that go along with it. Like it's not just like one thing. There's other problems with it. Does anybody know what it's called if you have a genetic disorder that causes your erythrocytes or your red blood cells to be misshapen and sort of crescent shaped rather than round? Do you know? Sickle cell anemia, right? Sickle cell anemia is a specific disorder. It's a genetic disorder, and it can cause your red blood cells, and they're supposed to look kind of like donuts, but the hole doesn't go all the way through, right? It's like you took a little round pillow and you mushed it on both sides. That's what a red blood cell looks like. But if you have sickle cell anemia, you get these little kind of crescent or sickle shaped cells, and they don't hold enough oxygen. And that results in extraordinary pain. It causes pain pain crisis is what they call it. And it's so bad that some people can't, like, they can't go to work. Like it's really terrible. I worked with a girl that had sickle cell anemia once, and it was awful, awful. She struggled a lot. So yeah, you need those things to function how they're supposed to function. So equilibria involving complex ions. In an aqueous solution, a complex ion exists in equilibrium with its components, the central metallic ion and the ligands. That's what we call the little guys around the outside, the ligands. Complex ions are formed when Lewis bases, which are ligands, attach themselves to metal ions in solution. The formation of complex ions can substantially increase the solubility of sparingly soluble salts if the complex ion has a large K sub F. So K sub F. This is something I'm not gonna get crazy picky about this, but I want you to know about it. Okay, this is one of those ones like know about it, but I'm not gonna make you do like 100 problems involving it. But your K sub F is a constant for a given solvent. K sub F is called the molar freezing point depression constant and represents how many degrees the freezing point of the solvent will change when 1 mole of a non-volatile, non-ionizing, non-dissociating solute dissolves in 1 kilogram of the solvent. So this will tell you about the equilibrium and what to expect from the equilibrium. That's the point. All right, so here's a very quick and very weird but fun TED Ed. Yes, Wix, I know. Don't need this ad, I already have Wix. Okay.
Say two people are walking down the street.
This is a great metaphor, but it's weird.
They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now, you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the string, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now, the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually, they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No, well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. Well, we're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty traumatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
So face arm people, but it's a good metaphor. It works, right? At the beginning, you're gonna have, you know, certain number of face arm people forming, and they'll be forming more rapidly than the people giving the arms back to the faces. And then with time, you're gonna have less people donating arms and to faces and more people returning arms to bodies. And then you'll get a nice even amount. And the numbers won't change, even though people are still exchanging arms, basically. But I saw that and I was like, this is super weird, but I love it. So anyway, so systems at equilibrium. So if we talk about systems, all right. First, we got to understand what is dynamic equilibrium. Yeah. Oh, yes. This is Georgia Natural Gas. Yes. Okay. Always commercial snap. Okay.
Equilibrium, the conditions required.
Hello. Why did you do
In
that?
this lesson,
There.
you will learn about dynamic equilibrium, the conditions required for dynamic equilibrium to be reached, and examples of systems at equilibrium. Imagine you are digging a hole. You got it? Imagine, as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed, there would be no change to the size of the hole. The same concept can be applied to a reversible reaction. If the rate of the forward reaction, reactants to products, is the same as the reverse reaction, products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there is no overall observable change. For a chemical system, such as a reaction or a phase change, to be at equilibrium, it must meet two important criteria. First, it must be a reversible process. Second, it must be taking place in a closed system. A closed system is one where there is no exchange of matter, only exchange of energy. An example of a reaction at equilibrium is the reaction of hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentrations decrease as hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. Over time, the concentrations of hydrogen, iodine, and hydrogen iodide remain constant. So what is happening here? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both the forward and reverse reactions are occurring. This reaction has not stopped, but rather has reached dynamic equilibrium. What would happen to this reaction if the lid on top of the glass jar was opened? Please pause the lesson to think about this and resume when you are done.
Actually, we'll pause it. What do you think would happen if you took the lid away?
The gas will float away.
Gas will escape. Yeah.
Is there pressure?
Well, yeah, but if you took the lid off, you've got iodine, hydrogen, and then hydrogen iodide. And they're forming at the same rate. You got an equilibrium, but now you no longer have a closed system.
If the lid was removed, the system is no longer at equilibrium as the reactants and products or matter would be able to escape the system. Liquid bromine equilibrates to form gaseous bromine at room temperature. Remember that this is not a reaction, but rather a phase change. Phase changes can also reach equilibrium under the correct conditions. As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously at the same rate, there is no observable macroscopic change, but the system is in fact in dynamic equilibrium. In summary, a chemical system is said to be at equilibrium when the rate of the forward reaction is the same as the rate of the reverse reaction. There are no observable changes, but both directions of the reaction are occurring, so it is a dynamic equilibrium.
So who knows what a terrarium is? What's a terrarium, Jordan?
It's like a little area with plants. It's like a
With plants.
closed bottle.
Yeah, Andrew?
A closed ecosystem.
A closed ecosystem. Yeah, okay, that's a good thing to add. Closed, what else?
A closed system in which you control all variables.
Yeah, closed system where you're trying to control all the variables. That's the idea. So what you have there in a terrarium is you've got water in phase change, right? You've got water in gaseous form and in liquid form typically. And if you stress the system by changing the temperature, then you should expect to see more gas, right? More gaseous water. And if you decrease the temperature, you should expect to see more water in liquid form. And that'll happen because even though it's a closed system, it's not isolated. Why is it not isolated system? What's the difference between a closed system and an isolated system? Do you remember?
In a closed system, there's energy on it, but in an isolated system, there's nothing.
Right, in a closed system, you have energy that can go in and out. But in an isolated system, the idea is that no energy or matter can get in or out of the system. And those are more theoretical, right?
But it doesn't
So-
happen in space, right?
Yeah, there's certain conditions, but for our purposes here, it's kind of a theoretical deal, right? But if you have a terrarium, they're usually glass, sometimes they're plastic, but they're going to be impacted by external temperature. You're going to have energy, thermal energy, coming in and leaving that system. So you're going to have the water in there trying to fight for equilibrium at the given temperature at the given time, which is why you might see a terrarium look like it's raining one day and not the next day, right? All right, so equilibrium
And
does state as well as chemical. So what is our equilibrium constant? This is another one I want you to know. We're not going to get too picky about it. So K sub EQ shows if the reaction is favorable. So if it's very large, if your K sub EQ is large, what do you expect to see?
It's very favorable.
True?
It favors the product.
Right, concentration of the products is greater in the concentration than the concentration of the reactants. And the reaction essentially goes to completion. All or most of the reactants are used up to form the products. All right, now what if your K sub EQ, your reaction, your equilibrium constant, sorry, is very small? Yusuf?
It's less than fun.
Right, okay, so your concentration of the reactants is going to be greater than the concentration of the products, and the reaction does not occur to any great extent. Most of the reactants are going to remain unchanged, and there are a few products produced. So understand that your equilibrium constant has to do with if it's very large, you have a higher concentration of products, and if it's very small, you have a higher concentration of reactants. So what's this useful for? It's useful in predicting what you would expect to see as far as dynamic equilibrium goes in a given system. That's the whole point of it. When it's not very large or very small and it's close to the value of 1, you have roughly equal amounts of reactants and products, and they're present at equilibrium. So when it's close to 1, you have equilibrium.
0.
I don't think you get 0, honestly. So now you have K sub SP. We have lots of little constants today, right? This is a product constant, solubility product constant. So the solubility product constant, K sub SP, is what? What is it? What's it mean? Caitlin?
for a solid that is in equilibrium with the solids dissolved in iron.
There you go. So it's the equilibrium constant for a solid substance dissolving. So it's your solute dissolving in an aqueous solution. And it represents the level at which a solute dissolves in solution. Basically, how soluble is something. The more soluble a substance is, the higher the K sub SP. So if you want to know how soluble something is, you can look for a solubility constant. And because it's a constant, it means it's something that's you can look up, right? It's been done. So you can look it up. The solubility of a substance in a solvent is what? The total amount of solute that can be dissolved in the solvent at equilibrium. So on the other hand, your solubility product constant is an equilibrium constant that provides insight into the equilibrium between the solid solute and its constituent ions dissociated across the solution. So basically, most salts dissociate into ions when they dissolve, right? So there's an example of barium sulfate, right? And this equilibrium can be described, sorry, I couldn't speak for a minute, by a mass action expression, which is what this is right here. Not going to expect you to do too many of these, but I do want you to understand that your solubility product constant tells you how soluble something will be in an aqueous solution. That's the important bit. So how do we use it? Here's a way we use it. In making magnesium, if we want to make magnesium, so there's a process. We would first take calcium. This is how they do it. You can, one way to do it. You can take calcium carbonate and you decompose it into calcium oxide. So it's going to break down into its constituent parts. It's a decomposition reaction. You got calcium carbonate and it'll become calcium oxide plus carbon dioxide. The next part of the reaction here is they would take calcium oxide and it would undergo a synthesis reaction to form calcium hydroxide. So you take the calcium hydroxide, you add water, you end up with calcium hydroxide. Then what they would do is the calcium hydroxide is reacted with magnesium ions in seawater in a double displacement reaction, and the magnesium ions are separated from the other ions in the seawater, such as sodium, chloride, bromide ions. So you have calcium hydroxide plus magnesium ions, and you get magnesium hydroxide and calcium ions. And then they do another step. And the solid magnesium hydroxide is filtered out and it undergoes a neutralization with hydrochloric acid. So you take your magnesium hydroxide, and if it's hydroxide, it's a base because it has hydroxide in the name. And then you add hydrochloric acid. Now you're neutralizing it, and your product is magnesium chloride and water. Remember, always, if you put an acid and a base together and they neutralize, your products are always going to be a gas, a salt, and a water. In this case, you see your magnesium chloride and your water is what comes out of it. And then the magnesium chloride is dried and melted and decomposed through electrolysis to form magnesium metal. So now we want to get rid of the magnesium chloride to just have magnesium, and they break that down into magnesium and chloride separately. So you can start with calcium carbonate and go through this entire process, add some magnesium ions at one point, and you can end up with magnesium metal. So though those slightly soluble hydroxides are not salts, they have solubility product constant. So magnesium hydroxide is an example of this, and just shows how you can use that K sub SP for something practical. That's all. So equilibrium systems and stress. We stressed an equilibrium system in lab today. That's what we did. And here's what we did. We did Le Chatelier's principle. Oh, Le Chatelier. It's also known as your equilibrium law, Le Chatelier's principle. What's it say? Drew. Got to read your exact wording.
A system in equilibrium that undergoes stress will shift towards the side that is undergoing stress.
Yeah. Anything to add to that, or?
To simplify it, when a system at equilibrium is disturbed, the system adjusts to reduce the change.
There you go. Perfect. Both of those were good answers. So when a system experiences a disturbance, such as concentration, temperature, or pressure with what? Pressure applies to what? Gas, not solids or liquids. So when your system experiences a disturbance such as concentration, pressure, or temperature change, it will respond and restore a new equilibrium state. What did we do in lab? Which of these things did we stress? What did we stress? It wasn't pressure. What was it? Concentration. We stressed concentration. All right, so what's Le Chatelier's principle? If a stress is applied to an equilibrium system, the reaction will shift in a direction that tends to reduce the change. Oh, seesaw. He's tossing him off. Uh-oh, poor little guy. So, changes in concentration alter equilibrium composition. So, temperature affects equilibrium systems. If the temperature's increased, what happens?
It shifts the equilibrium in the direction of the endothermic reaction.
Okay, very good. It shifts the equilibrium in the direction of the endothermic reaction. And if it's reduced, the temperature's reduced, then what do you think will happen?
Shifts the equilibrium in the exothermic.
In the exothermic reaction. So this is how you can get, you can have reversible reactions that produce heat in one way and then absorb heat the other way. So you can see a temperature change in the reaction depending on which direction your reaction is going. Changes that alter equilibrium composition, pressure. Okay, pressure may alter systems in equilibrium. A pressure increase shifts the equilibrium to the side of the reaction with the fewer number of moles of gas, and a decrease will shift it to the side of the reaction with a greater number of moles of gas. So again, you get the same sort of graph if you were to graph the rate of a reaction. All right, so let's look at this. Why does this happen? So here's your stress. If you increase the concentration of a substance, it's going to shift away from that substance. Why? Caitlin, you want to? Yeah, so these deal with concentration. These are going to deal with pressure. And these are going to deal with temperature. So yeah, extra concentration is going to need to be used up. So when you're adding extra concentration, it needs to be used up, which is why it's going to shift away. So decrease concentration of a substance, it goes toward the substance. So if an increase goes away from the substance because extra concentration needs to be used up, then a decrease is going to go toward it because why?
There's not enough concentration.
Yeah, because it has a need to produce more of the substance to make up for what was removed. All right, so let's think about pressure. Increasing pressure in a system, it moves towards the fewer moles of gas. Why? Why would it move towards fewer moles if you've increased your pressure? Maybe it's like, I don't know. Because as your pressure increase is going to equal a volume decrease, right? If you put something under pressure, you're decreasing its volume. So it's going to move towards your fewer moles of gas. How about then if you decrease the pressure, it moves towards more moles of gas? Why do you think?
Pressure decreases, the volume increases.
There you go. Okay, because your pressure decrease equals a volume increase. So how about temperature? Your increased temperature of a system moves away from heat or energy, so it's an exothermic reaction is favored. Why do we think? It's because your extra heat and energy has got to be used up.
The opposite thing.
Yeah, it seems, yeah. And then your decreased temperature of a system is going to go towards heat energy, and an exothermic reaction is going to be favored because why? Where you go out, yeah, because you got more energy that needs to be produced to make up for the loss. And then if you add a catalyst, it's not going to shift. Okay, because what does a catalyst do? The rates of both forward and reverse reactions are increased by the same amount if you add a catalyst. So it's increasing it in both directions the same way. All right. So common ion effect. We saw this in lab, right? So if a substance having a common ion is added to an already saturated salt solution, for example, then some of the original salt will precipitate out as solid crystals, thus reducing solubility of the original salt, and we call it the common ion effect, and that's what we saw today in lab. So the common ion effect refers to, does anybody have a description? Anybody write it down? Anybody? The decrease in, oh, go ahead. Yeah, they have a common ion, yeah. So you get so you get a decrease in solubility of an ionic precipitate by the addition to the solution of a soluble compound with that ion in common with the precipitate. And this behavior is a consequence of Le Chatelier's principle for the equilibrium reaction of ionic association dissociation. If you have a solution and a solute in equilibrium, adding a common ion that's in common with the solid is going to cause what? What's going to happen? What happened in lab? Yeah, why was it cloudy? What did we get? You got a precipitate. Yes, yes. So decrease the solubility of the solute. And that's because Le Chatelier's principle states the reaction will shift toward the left, toward the reactants, and it will relieve the stress of the excess product. And then that's why you'll see your precipitate crash out of solution. Oh, here's our friend. Okay. He's going to give you a nice clear. Now he's going to show you all the mathy math that goes with this. I'm not going to make you do the mathy math that goes with some of this, but understand that you can do it. And here's how it works. Okay. But I'm not going to test you on it in particular.
I'm so excited about this. I actually haven't
He's going to med school. Good for him.
My first one.
Woo. Good for you.
We do business differently.
We had double commercials, a special.
We design and test our
Okay.
It's Professor Dave. Let's learn about the common
Professor
ion
Dave.
effect.
With the haircut. I don't like the haircut, Professor Dave. I like Shaggy Dave.
As we continue to learn about solubility and precipitates, we are beginning to understand ways that we can predict or even control precipitation.
Oh, look.
One such approach we must
Everybody's looking anyway. He finally figured it out. Ah!
Aboard.
Move slow, don't scare.
There was a woodpecker up there.
Yeah, I have a red belly wood, but this squirrel's been trying to get up here and figure out that bird feeder. And that's the closest he's gotten so far. So I'll check back after class and see if the camera caught him. And if it did, I'll put it in the forum for you. All right, so back to Dave, our buddy Dave. Sorry, what was the first thing you said there, Dave? There we go.
understand ways that we can predict or even control precipitation. One such approach we must understand involves something called the common ion effect. So let's learn precisely what this means. The common ion effect is an application of Le Chatelier's principle, which we learned all about in an earlier tutorial. So if you need to review, check that out now. Otherwise, we know that under this principle, which describes the behavior of equilibrium, if we were to add an additional amount of one of the components in an equilibrium, the equilibrium would shift towards the other side, using up some of that additional component and creating more of the substances on the other side. Let's now look at an equilibrium between, say, silver iodide and the aqueous silver and iodide ions. If we are interested in forming a silver iodide precipitate, one way we can do this is to add some potassium iodide. Potassium iodide shares a common ion with silver iodide, that being the iodide ion. If there is more iodide ion in solution, that will affect the equilibrium and it will shift left to use up the excess iodide ions. If the equilibrium shifts left, that means more silver iodide precipitate will form. So this is a method of promoting precipitation. Let's look at this more quantitatively. Cadmium sulfide has a KSP value of 1 × 10⁻28. If we place some cadmium sulfide in a 0.01 molar cadmium bromide solution, what will be the molar solubility of the cadmium sulfide? So first we must recognize that the common ion in this situation is cadmium, as it is present in both compounds.
Let's then set up an icebox for the cadmium sulfide equilibrium. We know the initial concentration of cadmium ion is 0.01 from the cadmium bromide, and there is no sulfide at first. Then a tiny amount of the cadmium sulfide will also dissolve, so we must add a change of X to each initial concentration to get our equilibrium concentrations, which will be 0.01 plus X and X. We can then plug these terms into the KSP expression, like so. Now, since the KSP is so incredibly tiny when compared with the initial cadmium ion concentration, we can consider X, or the additional concentration of cadmium that will come from cadmium sulfide, to be negligible. In other words, the equilibrium concentration of cadmium will certainly round down to 0.01. So let's just call it 0.01, which simplifies the expression considerably. Solving for X, since the sulfide concentration will be equal to the molar solubility of cadmium sulfide, we get a molar solubility of 1.0 times 10 to the negative 26. Without the cadmium bromide, the molar solubility would simply have been the square root of the solubility product, which would have been significantly larger than the value we just calculated. So the presence of the cadmium ions in solution has reduced the molar solubility and will thus promote precipitation. And that wraps up an introduction to the common ion effect. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to
Thanks,
email
Dave.
Professor.
Thanks, Dave. Yeah. Oh, yeah, everybody's there now. That's the red-bellied woodpecker. Yep. He's kind of an idiot. He really is. He's not very smart and he scares everybody else away. Everybody's just, see, they're all just waiting for their turn because they don't like to be there with him because he's a bully.
Lucky, they look sociable.
Well, they're flipped up to, oh, there's a pine warbler out there. It's a wren at the top. The one in the middle is a pine warbler. And the one at the bottom, I can't see if it's a purple finch. It's a female purple finch. So she's not purple, but that's what she is. And then on the rail is a female house finch. And that nitwit. He's there all the time. Ah, see, now he's gone. All right. So, practical uses of Le Chatelier's principle, aside from just making cloudy solution in lab. Fun, but how practical is it? All right, anybody have a mood ring? Oh, aren't they fun? They change color on you, don't they? They're never accurate, but they're fun, right? So it says these rings are advertised as to tell your mood, but in reality, they read your external body temperature. The thermotrophic liquid crystals in the rings arrange themselves according to temperature. The change in molecular structure establishes a new equilibrium and affects the wavelengths of light that are absorbed and reflected. As temperature increases, red and green light is absorbed and the ring becomes dark blue. Temperature is going to be your stressor for a mood ring, but mood rings are using Le Chatelier's principle. Now, I don't know how practical that is, but it's kind of cool. They're fun. How about the production of ammonia? Yeah, okay. We use Le Chatelier's principle when we go through this entire maze to produce ammonia. What do we use ammonia for? Cleaning. Cleaning, yeah. If you've ever used ammonia, it's pretty noxious. Uh-huh. Oh yeah? How are you gonna make it? Care to explain to your classmates who have not caught on yet?
Sit right here.
Just sit right here. Right there, in the kitchen. Yep. Yep. So yes, your body does produce ammonia. You do tend to pee it out. Yep. But also there's a certain process that can occur when you're working out called ketosis, when your body's in a particular state. Careful, y'all. And you can produce ammonia as a byproduct of that, and you can smell the ammonia. You will smell like ammonia. And it's really, really weird. It's very strange, but yeah, that can happen. This is called the Haber process, by the way. This process of making ammonia. And here's our dude, Le Chatelier, covered in Le Chat. Beaucoup les shots. Beaucoup de shots. 1, 2, 3, 4. Ooh, 5. I lied. Well, shot is cat in French, so somebody thought this was funny. So
So you didn't turn him into a rat.
Monsieur Le Chatelier is covered in, I did not turn him into a rat because he's covered in cats. Yeah, those are cool glasses. I like those.
It's covered in cats, why not? That's why.
So what evidence might lead you to believe that a chemical reaction is not at equilibrium? All right, Colin, what you got? Precipitate. Okay. Anybody else have anything different? Better. So any changes during a chemical reaction, such as changes in product or reactant concentrations and energy release or absorption, are indications that a reaction is not at a chemical equilibrium. So yes, the production of a precipitate would be a change in your concentration of your product or reactant, depending on what it is. In this case, it was our product, right, in lab. Did anyone attempt the solubility product expression for a slightly soluble compound of aluminum hydroxide? Aluminum hydroxide. Did anybody attempt it? If you had, it would look like that. That's your KSP. Okay, if a reaction could exist that had a delta H, so your enthalpy 0, what effect would temperature have on equilibrium? Did anybody give this one this one was a little tricky. It's not gonna, no change, right? All right, let's play. Oh no.
He adds Pharaoh.
What is Menti.com?
I got it.
Pharaoh.
He
adds Pharaoh. He adds Pharaoh.
And there may be a typo in it. Oh, go back. Here.
I found the brownie point that says he
Has,
adds
yeah, caught it.
Pharaoh.
Yep.
Do I have to write it?
Write it down, so I'll remember it. Everybody good? All right, so your first question. Where was Henry Louis Le Chatelier from? Excuse me. You never know.
It's French.
No, they speak French in Switzerland too. It's Swiss French. It's a little different. Like Swiss German is very different, but yeah.
Did it break?
And I need like.
Did it break?
Yes.
You broke
Go down. Can you use the soda
Okay, so your answer, Paris, France. He's a good old French dude. Le Chatelier with all his les petits chats. Your next one. When did he live? So how long ago was this guy doing reversible reactions? There you go. Okay, there it is. There it is. Did they rate?
1747.
1747. So October 8th, 1850 to September 17th, 1936. So this was a good while back. This dude was for real. Only one person got it right. Yep, that's what we were dealing with. Two people guessed it right. All right, good deal. Let's see what's the next one. What was the family business? Pharmaceuticals, metals, or agriculture? Finally, somebody says, oh, metal. Ah, two people say metal. Agriculture. Okay, so the family business. Whoop, wait a minute. There it is. So he was the son of a French materials engineer, Louis Le Chatelier, and Louise Durand. Father was influential figure who played important roles in the birth of the French aluminum industry and the introduction of the Martin Siemens process into the iron and steel industries and the rise of railway transportation. This is part of this, yes, that derives from the Siemens company, which is still around. It's an industrial engineering firm, Siemens. There's a giant Siemens tower off of 400. Have you seen it? Right? Yeah. We have a really good friend. He was one of our groomsmen at our wedding who actually went to work for them. And we talked about that in earth science or physical science? Because he was the project manager on the giant, over in Charlotte, they have a giant gas turbine power station. And he was the project manager on that. And that was done by Siemens, which is industrial engineering, which is a German company. All right, now, how about what kind of childhood did he have? That should say he was feral. That's the one that Caitlin just caught. Disciplined, feral, or raised by monks. Feral means wild. Was he allowed to run wild? Or was he disciplined, or was he raised by monks?
I mean, if he was raised by monks, he was probably disciplined too.
That's true.
Yeah,
Anybody know a feral child? I've met a few feral children in my day, and it's like, wow, yeah. That it brings free range parenting a whole new level, right? Feral is typically used to describe animals that are supposed to be domestic but are not, like wild cats. Cats that run around your neighborhood and don't have a home are feral. We have one constantly going through my yard. Beautiful cat, feral. So his mother raised the children by regimen that he described. He said, I was accustomed to a very strict discipline. It was necessary to wake up on time, prepare your duties and lessons, eat everything on your plate, etc. All my life, I maintained respect for order and law. Order is one of the most perfect forms of civilization. Order is one of the most perfect form, that's prophetic, of civilization. So he says right here, prepare your duties and your lessons. And we're talking mid to late 1800s. So very likely schooled at home like all of you, but probably like get your butt up out of bed, eat everything on your breakfast plate and start your work, crack, you know. Yeah. I think y'all would have been afraid of his mom. I think I would have been afraid of his mom. Right? So how about Henry Louis's brother, Alfred, was an expert in which things? Ceramics, railroads, and Islam, copper, porcelain, and woodcraft, or Hinduism, meditation, and Eastern medicine? Copper, porcelain, and woodcraft. Family business, yeah, metal, Hinduism, meditation, Eastern medicine. What do you call someone who has expertise in a bunch of varied areas?
Polymath.
There you go. Everybody remembers that. Yeah, jack of all trades. Polymath, that's the word we're looking for. A lot of scientists for polymath. So his brother, Frederick Alfred Le Chatelier, was a French soldier, ceramicist, and Islamologist. Spent most of his military career in French African colonies. After leaving the army, he was involved in a project to build a railway in the French Congo. You know, there are parts of Africa that speak French, right? Because they were colonized by the French. He fought a duel and killed his opponent over mutual accusations of improper conduct concerning Congo railways.
What?
Yes, let's get in a fight over improper conduct for Congo railways and kill one of our staff. Let's do that. He founded and ran a ceramics workshop for a few years before becoming a professor of Islamic sociology at the Collège de France from 1902 to 1925. This is an interesting dude. And then he exerted considerable influence over French policy towards the Muslim subjects of French colonial empire, arguing for policy based on solidly documented facts and tolerance and sympathy to rapidly changing Muslim societies. What an interesting dude. Yeah,
There was a war over a bucket.
I'm sure. What war was this?
The bucket war.
The bucket war.
It was a real thing.
Yeah.
Where is this one? I don't know this one.
Europe.
In Europe, over a bucket.
Yep.
A single solitary bucket.
Yep.
There have been wars fought over dumber things, but still. So this guy had a really deep understanding of Islam, which was very helpful because they were the French colonists were down in that area of the world. And so he helped with some tolerance and law policy creation and things that were probably the kind of thing that we would look at today and go, good job. You know, you're being inclusive and you're being kind and empathetic and not, you know, coming through and just tearing stuff up like people did so often. All righty, how about this one? In college, Henry Louis studied what?
Carrots.
Carrots. Always. Skibbity Sigma. Thanks, Andrew. How did I know? Science, Sigma Ohio Riz. Carrots. Science stuffs and chemistry.
Science and chemistry.
Ooh, who wants to define that one? Umramatology. What is it, James?
It's actually your mom.
Your mamatology. Okay. Now I get it. I was like, Ermamatology. I don't know that one. Okay. Your mamatology. I like your mamatology. Rock science, keratology. Whoop, whoop. People, what were they? People history. Dave. Oh boy, that's a lot. And there's some I can't even see and can't figure out how to see them. So engineering, primarily. I used to have, when I was in college and I was an RA and I was responsible for a whole hall of freshman girls, I had a sign on my door that said Nacho Mama, because that's all they ever wanted was me to like baby them. How do I do laundry? I don't understand. Why did I turn my underwear red when I washed it with red socks? Well, you idiot. You know, that kind of thing. So, oh, plenty of people get to college and they don't know how to do laundry. They don't know how to shop. They don't know how to turn on a vacuum. It's amazing. It's amazing. People get accepted to selective universities and don't know how to do those basic things. I'm telling you, I promise you, you'll get there one day and go, what is wrong with these people? But they have like, 1580 SAT score, but they don't know how to run a washing machine. It's a thing. It's a thing. All right. So engineering primarily. So at Collège de France, which of the following courses did he not teach? So you've got phenomena of combustion, theory of chemical equilibria, high temperature measurements, and phenomena of dissociation, properties of metal alloys, iron alloys, general methods of analytical chemistry, molecular modeling and isomer studies, general laws of analytical chemistry, general laws of chemical mechanics, silica and its compounds, some practical applications of the fundamental principles of chemistry, or properties of metals and some alloys. Lots of choices.
She's not everything.
Yeah, there's one of these he did not teach. Somebody's gonna win this one. If you're the winner, admit to it, because it's pretty good out of all those choices. Whoop. So he never taught molecular modeling and isomer studies. But he taught all these. So yep, silica and its compounds. He taught lots of things, obviously. You would expect him to teach this one, right? Theory of equilibria. Dude has an equilibrium law named after him. Okay. What common tool owes its invention to a paper written by Le Chatelier? A hammer. There you go. All right. Yo, mama. Good one. Luigi. Carrot. Carrot's a good tool. You can use it for lots of big things. That is a tool, for sure. You can use it for things. Yep. Bread. Toilet paper. Would be good. Doggo. Fire. Filter paper. Okay. No, I can't make it click. Responses. Can I see him this way? Does it show them to me if I go that way? I don't know. Oh, it's doing something. Woohoo! Woohoo! I don't know, hang on. I'm seeing if it's going to show me the rest of the responses. Oh, no, it's the same things. I don't know how to see them. It won't let me. Every time I scroll, it goes to the answers. So on the advice of a paper of Le Chatelier, the combustion of a mixture of oxygen and acetylene in equal parts rendered a flame more than 3,000 Celsius. And in 1899, Charles Picard, not related to, Star Trek Picard, started to investigate the phenomenon, but failed because of soot deposits. In 1901, the latter consulted with Edmond Fouché, and together they obtained a perfectly stable flame, and the oxyacetylene industry was born. In 1902, Fouché invented a gas welder tool with French patent. There's your number. And in 1910, Picard developed the needle valve. So oxyacetylene welding torches. Thank you, Le Chatelier. If it's welded with oxyacetylene, which most things today are welded with, thank you, Le Chatelier. Who knew? Le Chatelier deeply regretted his career failure to synthesize what? What was he trying to synthesize? Gold, ammonia, diamonds, ozone, or a stronger train rail material. I'd be trying to synthesize some diamonds if it were me, and some gold, but that's just me. Not really anything to synthesize with the diamond. It's just carbon. Or gold. Could do that.
I always put something on top. A medium is at the first place. A medium.
It's just the average.
Yeah, this is the rank. How people have selected them. What's most likely? What's the, highest answer here? Ooh, still shifting.
Oh, why is that big?
So in 1901, he attempted the direct combination of two gases, nitrogen and hydrogen, at a pressure of 200 atmospheres and 600 Celsius in the presence of metallic iron. An air compressor forced the mixture of gases into a steel Berthelot bomb, where a platinum spiral heated them and reduced the iron catalyst. A terrific explosion occurred, which nearly killed an assistant. Le Chatelier found the explosion was due to the presence of air in the apparatus used, and thus it was left for Fritz Haber to succeed, where several French chemists, including Thenard, Saint-Clair Deville, and even Berthelot, had failed. Less than 5 years later, Haber and Carl Bosch were successful in producing ammonia on a commercial scale. Near the end of his life, Le Chatelier wrote, "I let the discovery of the ammonia synthesis slip through my hands. It was the greatest blunder of my scientific career." What a blunder. Got a law named after you. Oxyacetylene torches, you blunderer, you. Anybody Haber is the name for the process for producing ammonia. I showed it to you earlier. It was called the Haber process. How about Bosch? Anybody know that?
Make bridges.
They might make fridges. They make all Bosch is still like Bosch and Lomb. Like they make contact lenses and things. Like Bosch and Lomb is a huge company. It's still a huge. So some of these guys that you're starting to see in these industrial processes, Siemens, Bosch, Haber, they're all still in use. Like they're all still active today. Some of these companies are like really old and still going. All right, so y'all are nuts back there. Okay, so you're just gonna take today's lab and file it. Be sure, did all my lab team captains turn in a lab?
I did.
You did? You did?
We don't know.
You did? That's 3. I know PJ did. That's 4. So that's all of them. So that's done. Good. I am putting it in your weekly email, but I'm gonna be out of town Friday, Saturday, Sunday. So don't email me because I'm probably not gonna check email much. If you need me, text me. Think we're good. Are we good, people? I'll move your money up here. Got a little extra time today, but that's cool. BBC News. Aren't they adorable? She did such a sweet job. That was so nice of her to do that. It was very sweet.
Why'd you put Skibbity Red?
Uh-huh.